Okay, here's the same problem that we already worked, but this is kind of the last layer of what you have to do, and this is probably the harder part, actually, is you need to be able to take these pictures that you've drawn when you simplify the circuit and work backward through them to figure out what is the current and the voltage that's associated with each resistor. This last part here is power. Power is, you probably remember, current times voltage. So actually that's an easy last step. If I just fill these in, I just can multiply them to get the end, the power. So let's work backwards through this and say, okay, we started off here by saying there is 1.9 amps. So that was 1.9 amps leaving the battery going through that one. So then I can step back a picture and say, well, these two in series act the same as that one. So this is exactly the same amount of current going through here, 1.9 amps. Well, the 3 ohm resistor is one of the resistors in my original picture, so I can go to my chart and say 3 ohm resistor, 1.9 amps, and fill that in. I could then say, well, what is the voltage that goes with that guy? Well, the voltage across that is going to be, if you just think about Ohm's law but rearrange it, V equals IR, just the current times the resistance. So 1.9 times 3 is going to give us something just shy of 6, which is 5.7. So I can go to my chart here and write in, okay, that's 5.7 volts. 5.7 with that guy. So that resistor's done. Now I go to this one and say, well, it has the same current through it. So even though it's not a real resistor, I can find the voltage, which is 1.9 amps times the 3.2 ohms of equivalent resistance. And that's really 6.1 volts across that one. Now that's not a real resistor, so I can't put it anywhere on my sheet, my chart here, but I can back up and say these two in parallel act the same as the 3.2, so they both have the same voltage of 6.1 volts across them. They are, well, closer to real resistors. The 5 is a real resistor. So I'm going to go to my 5 and say the voltage is 6.1 volts. And then if that's 6.1 volts divided by 5 ohms of resistance, this is just Ohm's law. 6.1 divided by 5, and I get 1.22 amps, which I can write that in my chart. Now I step down here and say, well, what is the current through the 9 ohm? So I can do Ohm's law, 6.1 volts divided by 9 ohms, and I get 0.67 amps. And then I can step back a picture and say the 7 and the 2 act the same as the 9, so they have the same current, which is 0.67 amps going through that. So I can figure out 0.67 amps there and write it on my chart, 0.67 amps there, because they are real resistors. And now it's just left to find the voltage across it, each one. So current of 0.67 times 7 ohms of resistance, I get 4.7 with rounding. And the other one, when I times 2 by 0.67, I get 2 times 0.67, 1.34, that sounds better, volts across that. Now my last step really to find the power in watts is just the current times the voltage. So 1.9 times 5.7 is 10.8 watts. 1.22 times 6.1 is 7.4 watts. 0.67 times 4.7 is 3.1 watts. And 0.67 times 1.34 is 0.8. And really that's 0.9 watts. So that tells me that the one that's dissipating power the most is the 3 ohm resistor, really because it has the highest current and a pretty high voltage, but current affects things power more than the voltage does. So this one would be the brightest if these were light bulbs. If they were just resistors, it would be the one that gets the hottest, the one that transfers the most energy. This would be second, this would be third, and that little one would be blast. Now there are ways to check it, but I won't go through that with you guys right now.